The key function of a solar receiver is to absorb as much solar energy that is reflected from the mirrors as is possible. So light, once reflected from heliostats, gets beamed up to the solar tower, and the first thing it sees is this absorber coating on the outside of these tubes that are carrying the heat transfer fluid or molten salt.
Those plants are supposed to work for decades. And currently, the state of the art are some coatings that were developed by NASA for space applications. They're very durable, but after 1-2 years, they start degrading, they start peeling off. The ability to capture light and turning into heat, it starts decreasing with time until they fail. And these receivers are not on the ground, they're 200 meters above the ground.
This is the ANU's high flux solar simulator. We use it to test our coral structure coatings durability. We wanted to put our coatings at a high flux with this equipment to see how its absorbance and mechanical stability change over time. At the first part, we keep the sample temperature at 800 centigrade. Then when it reached to that time that we need, we close this door automatically, and the amount of flux is going inside decreases and the sample's temperature drop.
You might have 1,000 kilowatts per metre squared as a flux on a receiver, on a coating like this. Then all of a sudden the cloud bank comes over and you see, drops in temperature of, several hundred degrees. Of course, with thermal expansion, thermal contractions, you're seeing a lot of stresses that are forming both in the materials but also in the coatings. So you need to have coatings that are very robust in these types of conditions. And that's actually one of the real nice advantages of this coral morphology. The fact that the structure is not just a planar, flat structure that needs to expand and contract, but actually acts as almost like a kind of like a spring. And when the material underneath is expanding and contracting, the coral structure above is very forgiving, relieving some of those stresses in the coating. And that's, I think, partly why it's been proven to be such a robust coating in this type of testing.
If you're able to rotate it so that the light of the sun comes from the side, you're able to see the little shades. The macro scale is a coral-like morphology. The micro scale is another coral-like morphology, mimicking the micropores of those corals. And we also have something called a nano scale, because we need to have light trapping at different length scales.
It has a higher absorbance at the first time compared to the previous coatings, pyromark, so it has higher efficiency and it's stable and it's not degraded as fast as the other coatings, so it can be stable for a longer time, so we don't need to repaint the systems, so it reduces the cost.
Hi, my name is Kaoru Tsuda. I'm a CEO of Nano Fronteir Technology. I'd like to introduce our development history. Since the founding of Nano Fronteir Technology, we have focused on the development of nanomaterial composite. In 2015, we started joint research with Shinshu University. By mixing metal oxide and our nanomaterials, we succeeded in creating new coating with pores. These pores incredibly improve light absorption. We had many discussions with Professor Murakami and Mr. Kobayashi at Shinshu University about the ink composition and continue to improve the ink. Using improved ink, Nano Fronteir Technology underwent countless application tests over and over again. After repeated improving the coating ink and conducting countless coating experiments, we finally arrived at current state. Collaborative research with ANU began in 2017. Professor Joe Coventry and I met at the SolarPACES in Abu Dhabi. Even though my research was not completed at the time, and I have not any presentation, he interested in our coatings. Our joint research began from there. I'm so grateful to the SolarPACES organization for creating such opportunity. ANU had a lot of knowledge about CSP. We were able to make more practical developments. They conducted various tests, long-term aging tests, cycle aging tests, and on-site testing, and they also had a detailed analysis on the samples. As a result, our development accelerated rapidly. We continue to make further improvements by feeding back the results of ANU's analysis to Shinshu University. The coating we have developed with a coral-like structure has the highest absorption and highest durability of any solar absorber coating currently available. The result was published in Energy and Environmental Science in 2022. These excellent results could not have been achieved without the cooperation of Shinshu University and ANU. 私はこのように長く続けてきた研究結果がようやく認められて本当に嬉しく思っています。私たちはこれからも CSP の発展のために研究開発を邁進し、実用化を目指していきます。ありがとうございました。